Okay, in this video we continue our study of how to use the residue theorem to evaluate complex integrals. These are the examples we're going to work through. We're going to do A and B, and then we're going to give you an opportunity to do C, D, and E. This is a summary of the residue theorem, which says the integral of f of z around a simple closed contour C is 2 pi times the sum of the residues of f at singularities inside C. So starting with this one, the first thing we are going to do, so this contour here is a circle centered at z equals to 2 plus 3i. We said you always obtain that by taking this thing and equating it to 0. The radius is going to be 4. Okay, now the residues or the singularities function is going to be singular from this term at plus or minus 2, and from this term plus or minus 3i. So let's just make a sketch of how this is going to look like. So we have got singularities at 2 minus 2, and then 3i minus 3i, and then the contour is centered at 2, 3i. It's got radius 4, so that means if this is 3 here, it's going to be going up to around this point, and it's radius 4, so it's going to be tangential at the point which is vertically above that singularity. So the circle is going to be something like this. So that's going to be our contour. Okay, from this sketch, the only two singularities that are going to be inside are 3i and 2. But just to be sure, okay, this distance here is going to be the square root of 3 plus 4. So that distance is going to be 5. That means this one is definitely outside. And then this distance here, so this side is going to be 6 and this side is going to be 2. So that's going to be the square root of 36 plus 4. It's going to be the square root of 40, which is definitely more than 4, because 4 is the square root of 16. So the only singularities that are inside are 3i and 2. So we need to work on the residues of this function at 2 and 3i. So if we start with the one at 2, what we're going to do is we're going to use the formula for the residues of a function which is a rational function. So we're just going to differentiate the denominator. So 2z here, z squared plus 9 plus 2z into z squared minus 4. The numerator just remains z. And then we're going to plug in z equals to 2 here. So when we do that, 2 squared in the numerator is going to give us 4. In the denominator, this term is going to vanish. So we're just going to have 2 times 2, and then 2 squared plus 9. So this is going to be 1 over 13. Then at 3i, so the residue at z equals to 3i. So we're going to use the same expression as this one, but this time we're plugging in 3i. So 2z z squared plus 9, 2z z squared minus 4. This, by the way, was obtained by just simply differentiating this using the product rule. So this time we're plugging in z equals to 3i. So when we do that, 3i squared is negative 9. This term is going to vanish, so we're just going to have that term there. So it's going to be 2 times 3i minus 9 minus 4. So we're going to have minus 9 over 6i. Let's just keep it as it is. So it's going to be negative 2, 3i, and then 13. 3 goes 3 times here. That becomes positive. But if you take the I to the numerator, so that whole term becomes negative again. So it's going to be negative 3i over 26. So that means the value of our integral, if we call this thing I, so I is simply going to be 2 pi I times 1 over 13 minus 3i over 26. Then, so this is going to be 2 pi over, if we factor out 26, that's going to be 2 minus 3i. So this is going to be pi over 13. So multiply the I into the brackets. So that's going to be 2i plus 3. So that's going to be the value of our integral there. And then now going on to the second example. So in B, we have got the integral around the unit circle of z cubed cosine of 5 over z squared. Okay, so z cubed here, cosine of 5 over z squared dz. So here clearly z equals to 0. So that is our contour unit circle centered at the origin. The singularity is at the origin because this term is going to be singular when z equals to 0. So that's clearly inside. So we just need to find the residue of this function at that point. Now, first question is, what type of singularity do we have here? And since this this expression is not exactly like this one here, where we have got polynomials in the denominator. When we've got polynomials in the denominator, this is pretty easy to determine the nature of the singularity. But here, this is a cosine. So what we're going to have to do, we're going to have to resort to a Laurent expansion of this function about z equal to 0. So that means just expanding this in terms of the Taylor series of cosine at the origin. So Taylor series of cosine at the origin looks like this. Of course, the radius of convergence of this is infinity. So for this problem, we are going to have z cubed. The first term of the cosine expansion is 1. Then the second term is u squared. So this time this is going to be 5 over z squared squared. This is over 2 factorial. The next term is going to be 1 over 4 factorial. 5 over z squared to the power 4, etc. For our purposes, this might be good enough. we will see if it is not. So this is going to be 1 minus 25 over 2z to the power 4 now. And then this is going to be plus 5 to the power 4 is 625. Going to be 4 factorial, which is 24. So 24z to the power 8 here. And then this goes on and on, multiplying through by z cubed. So the first term is going to be z cubed. Then the second term is going to be minus 25 over 2z. Then plus 625 over 24. This is going to be z to the power 5 now. This clearly shows that the powers of z that are negative are going to go on and on and on here. So it is telling us that z equals to 0 is an essential singularity, or this is a pole of order infinity. So we don't have a formula for that, and in fact in our video where we discussed the nature of or the formulas of how to find singularities, we did mention that for a pole of order infinity, the best way to extract the residue is via the Laurent expansion, which we already have here. So from the Laurent expansion, the residue is simply the coefficient of the term with power -1. So in this case, that's 1 over z. So the residue at 0 is simply -25 over 2, which means the value of our integral, so I'll call this I. So therefore, into the value of our integral I is going to be 2 pi I times -25 over 2. This is going to be -25 pi I. Okay. So at this point, we're going to give you an opportunity to have a go at the next 3 problems here. So C, D, and E. You can pause the video, work through these ones, and then when you continue the video, then you can compare with our solutions. All right, we're now going to scroll down to our solutions for part C, D, and E. We would like to thank you for visiting our channel and watching this video. We do hope that this material is helpful to you. Of course, we ask you to subscribe to our channel to support the work that we do, so that we can produce more videos. If you've got any questions or comments, please just post them in the comment section below. So for C, this is the integral we have got. And that is the contour. If you equate this to 0, you get z equals to -1 plus I. So that's the center of our circle. The radius is 3. So this is obviously going to be inside. This is also going to be inside, because this is 2, this is 1. So that means this distance here is square root 5, which is smaller than square root 9. This one though is going to be outside, because this is 3. 3 squared is 9, and this is 1, so this is square root 10. So this one is just outside the contour. This distance here is square root 10. So the these three singularities are going to be inside our contour. So if we just differentiate these and then plug in z equals to -1, we can find the singularity at z equals to -1. This term vanishes. This one becomes -2 times 5. That becomes I over 10. The e to the -I pound 2 is just -I. If we do the same calculation for z equals to 1, the numerator comes this, the denominator becomes this is I and this is just 10. So the two of them are actually equal. And then for 2I, which is the singularity here, so again, if you plug into I, this term is going to vanish. This is going to be 4I, this is going to be negative 5 there. And then the numerator is just going to be e to the minus pi. So it's actually going to be a real quantity. So if we take I up here, this just becomes I e to the minus pi over 20. So the value of the integral, so we'll call this I here, it's just going to be 2 pi I times the sum of all the residues. So if we simplify here, we end up with this expression there. Okay, for this one, the singularity at z equals to 0 is inside our given contour, which is a circle. Unit circle centered at the origin. We are going to use Laurent series, expand this, and then that's going to tell us what type of singularity z equals to 0 is, especially because this is also 0 at z equals to 0. So if we do that, we find that the singularity is a pole of order 3, and the residue, which is going to be the coefficient of 1 over z, is negative 4/3. So that means the value of this integral is going to be 2 pi I times negative 4/3, and that gives us the final value. This one again is singular at z equals to 0. We appeal to the Laurent series, and we find that it is a pole of infinite order, because the negative powers, you can see, are going to go on infinitely here. So pole of infinite order is also called an essential singularity. And again, the coefficient of 1 over z is going to give us our residue. And so the integral is going to be negative 9 pi I, if we call that I. All right, thank you.